So the plan for tonight is to do two somewhat smaller features of Python 3.8. The last two streams we were busy doing the walrus operator, or the named expression, which turned out to be a little bit more complicated than I had understood when we started. And what I want to do tonight is to add a small feature in 3.8 that shows a somewhat different part of the PyPy interpreter. And what I want to do is I want to implement this feature here, which is called add as integer ratio to int objects. And we can first play a little bit with Python 3.8 to understand what it does. So it's basically a generalization of a feature of a method on floats. So if you have some float, you can say as integer ratio, and then you get basically two integers, and the float is close to basically the ratio of those two integers. Right. And the same thing is now added to integers. And of course that's boring, because what you do is, okay, completion can't deal with integers, it seems. Integer ratio. You always get 1 in the second part of the tuple, and simply the integer in the first part, because the integer as an integer ratio is the integer divided by 1, so it's a little bit boring. Hello Tobias, nice to see you again. And then the same method exists on other numerical on other numerical types. I think it exists on decimal. Capital D. I never used the module, right? Right. Let's try. I'm not sure it exists on complex numbers. Seems not. Doesn't really make sense. Right. Anyway, so the feature is relatively simple. We're going to add this method to the integer class, and the reason why I want to do it is, hi Arthur, I want to look a little bit at how the objects in the built-in objects in PyPy are implemented, and how the types of the built-in types are defined. And we can use this very simple method where the method itself is not very hard to implement. Hi Panos. Yeah, but we can see and understand a little bit more about how the objects work and how they're represented on the RPython interpreter level. And yeah, so let's get started. So what we can do is if I had no clue how the PyPy worked, I could grab for as integer ratio, because the implementation is already there for floats. So basically we can look at what the float code does, and then go there and basically copy that for and do something very similar for integers. And all of that happens in a directory called object space standard, and there's a test for the behavior, and then there's an implementation. And the file that contains the implementation is called floatobject.py. Maybe not that surprising. And we should check whether there's also an int object.py there. So let's go there. It's called an object space for a little bit pretentious reasons. The object space is basically the library of object operations that the interpreter implements. And if you look here, there are all the objects in here that you would expect. There's a bool object, there's a byte array object, bytes objects, a few strange things: complex objects, dict object, float object, int object, iter object, and so on. So those are all the built-in object implementations. And we can look at floatObject.py. Wait, I have a Vim open. Like this. And there's a scary number of imports. And then there's some helper functions. But most importantly, there's a class called w_floatObject, which inherits from wroot. What the w means, I'm going to explain in a moment. And that is basically a class, and the instances of that class represent floats in the Python interpreter. And a float object is basically a very simple object. It takes a float value and it stores the float value in a field, and that's the whole object. Right. And then there's some special stuff. There's a declaration that the float value field of that instance is immutable. That means once you initialize the object, you cannot change the field anymore, which isn't really standard Python. That's more of an RPython extension. And then there's a ton of methods here. Right. And so we can search for as_integer_ratio here. And then we find this desker method, which means describe or descriptor or something. And that's basically the implementation of the as_integer_ratio method in RPython. And here's the doc string. And what it does is it takes the float val attribute and it calls some helper function that is called float as rbigint ratio, which gives a numerator and a denominator. It can also raise an overflow error, and then it needs to convert the exception and the value error. And then it, if there's no exception that's raised, then we turn the numerator and denominator into wrapped instances again by calling this space function newlong from rbigint, and we do that twice, and then we make a new tuple, calling new tuple with the two elements, and that's it. So there's a lot of things that are hard to understand here, but the basic approach is we have a method on the implementation class that corresponds to the method on the Python level. And that mapping between the Python level and the RPython level is done further down. It's done by something called a type def, and a type def is basically an object that defines the type. It gives the name of the type and the base class. In the case of float, that's just object, so it isn't given. The doc string for the type, and then a list of all the methods. And for as_integer_ratio, there's some magic gluing stuff that says if you call as_integer_ratio on the Python level, then it gets turned into a call to this method on the implementation level. And I mean, CPython has equivalent stuff. You have the type definition there in C, and there it would. I mean, mentally, it's always a little bit easier if you do that in C, because then the languages are clearly distinct. So in C, this function here would be implemented in C, and it's kind of obvious that you can't just map methods on the upper level to methods on the lower level. But here, it's a little bit confusing because both levels are Python, and we need to force ourselves to kind of separate the two. Right, so what's all the W stuff? So W means wrapped, and it's basically a syntax convention that we use to distinguish objects that exist on the Python level, on the application level. So a W float object is basically a class that represents instances of just float on the upper level. And then every time we have an instance of that, we use lowercase w num. So this is a wrapped long, and this is a wrapped long, and we call space.newTuple, which will return a wrapped tuple. So what about the space? The space is basically an object that we sort of pass around everywhere through the interpreter, and it's basically the entry point for doing all kinds of operations on objects. And it's used to create new longs twice here, and it's used to create a new tuple here. Right. Okay, so let's basically copy that. The same kind of approach for integers, and we start by saying by opening this, and then we go somewhere to the bottom. I suppose upTestInt is promising, and we do something like where's the end of that class? Here. Def test hi Matti. Int as integer ratio, and we can do something like start simple, assert for dot as integer ratio equal 4, 1. That space here is needed because otherwise the parser is confused and it thinks that this is a float and not a method call on an int. So if you wanna call a method on an int, you need to put a space in here, which was something I didn't really appreciate until very recently. Okay, so that's kind of the very simplest test that we can write, and then there are various corner cases that we might want to think about later. And let's maybe also do a negative number, and I think the minus sign is in the numerator. Okay, and I think that's kind of enough as a first test. And if we run that, wait, test int object, integer ratio, and of course it won't work, but we should make sure that it doesn't work because otherwise we misunderstood our task. Let's see, it takes a while as usual. Right, and it fails. There are several subclasses of this class, I think, so we get 2 failures. I should have run it with -x. Let's see. Right. But it fails the way we expect it to. It fails by saying int object has no attribute as integer ratio. Okay. So let's actually open int object. And in here we see a class called abstract int object, and it has various methods, and including stuff like power and hash and stuff like that. And what we want to do is we want to add a new one, desker as integer ratio, takes itself in a space, now we need to implement that, and implementing that is relatively easy. What we do is we say return space.newTuple. It always returns a tuple of 2 elements, and the 2 elements are self, the first element, and space.newInt 1. Yep, that should be it. Right, so that's the implementation, but we still need to sort of connect the dots and say the upper level as integer ratio method needs to be turned into a call to this implementation level method. So we need to find the type def, which is not here. That's interesting. Why not? Ah, it is here. Because I was searching with the wrong capitalization. Right. It has, that's interesting. It has a numerator and a denominator method. So maybe we should call those instead in the as integer ratio method. And then we can copy a little bit again what float object is doing. Where is it here? Right. Right. Abstract int object dot as integer ratio, and that's fine, I think. Right. I'm going to tell you in a couple of minutes why there's an abstract base class for integer objects. Right. But let's start the test first. Because I can talk while we wait. So integer objects changed quite a bit in Python 3. Before Python 3 and Python 2, there were two kind of different integer types, int and long. And the int type was for integers that fit into a machine word. So 2 to the power of 31 minus 1 on 32-bit machines, and 2 to the power of 63 minus 1 on 64-bit machines. And when some arithmetic operation goes out of the bounds of that range, then it would automatically convert to a big integer representation that is basically able to represent arbitrarily large integers. And that was that was observable for the programmer. And our test passed, but let's talk about longs a little bit first. This is a Python 2, so if we say something type 2 is int and type 2 to the power of 100 is long. And in Python 3, it happens completely transparently. So the long type is gone, and if it overflows, it will internally change its representation rather drastically. But from the programmer point of view, you can't really see that one of them is implemented by storing the number in a machine word, and one of them has a more complicated representation using many digits of some large base. But in what we do in PyPy is we represent, we implement this by having an abstract int object base class and then two different subclasses of this class. So we have, let's look for the subclasses. Int object. We have an int object, and that's basically a class that stores a machine integer, a machine word sized integer, and then all the operations operate on that machine word. And then there's also another file that has a different subclass of that, which is called abstract long object, and there's also a concrete implementation of that down here called wlong object, and it has a field called num, which is an instance of rbigint, which is a class that is able to represent arbitrarily large integers. Right, and then depending on whether the number fits into a word, it will either represent the number by using an instance of wint object, and if it doesn't fit into a word, it will use an instance of wlong object and use an rbigint with all the digits of the long of the big number that you want to represent. But the type of both is int, and that means in particular that all the methods for both of these implementation level classes at the application level, at the upper level, come from this type def here. Wait, where are we? Here. So all the method implementations come from here, and right, and they will dispatch to the right implementation on the implementation level depending on the class that we have. But our integer ratio implementation works for both representations, so we don't need to do anything special about that here. So let's actually look at what get numerator does. That's weird. There's some strange meta-programming magic here. Right. Interesting. There's a number of methods that all return the integer itself. So there's pos, which returns the integer itself. There's index, which returns the integer itself. There's trunc, which cuts off the non-existing decimal points, so it just returns the integer itself. And floor and ceil and numerator and real. So there's a small helper function here that creates all these methods. And they're all implemented in the same way by just returning self.int of space. And maybe actually we should do that too. I'm going to think about that for a moment. So our first set of tests passes. There's another, given that we now talked about longs, there's another test that we should write. We should make sure that if we have a number that's too large to fit into a machine int, and we call as integer ratio, it should still work. Try that, it's bound to work. And then there's another thing that we should think about, which is what happens if we, let's go to, what happens if we run this on a subclass of int. So let's say we have a subclass of int that doesn't do anything, and we call, we make an instance of that. And then we call as integer ratio. Then we get two things. And the numerator is 5. The question is, what is the type of the numerator? It's int. So even though it has the same value as the subclass that we passed in here, it gets turned into an instance of int. And that's one thing we're missing. So we need to add another test. That happens quite regularly. So even if you have a subclass of int and you add two such instances, you will still get an instance of int as a result and not of the subclass. So let's say we make a class x of int pass, and then we need to say a equal x5, d and d equal a dot as integer ratio assert n equal 5 and d equal 1 assert type of n equal int is int, right? Okay, and there's also another obvious subclass of int that we can test that's built in, which is bool. Bool subclass is int. Yeah, sorry, let's be slightly less sloppy. Thank you, Matti. Right. Another subclass of int is bool, so we should be able to say true dot as integer ratio, and we get 1 1, right? False should be 0 1. And in both cases, we probably want to check the types again. So like this, assert dn equal 1 1, and assert type of d is int. Right. And the same thing for false. And like this. Oops. Yep, that looks sensible. Okay, and I think those actually might fail right now, because if you look at the implementation again, where is as integer ratio? Wait, let's actually run them. But I suspect they might fail because we return self here. So in the example of true, we would just return true here, which is wrong, of course. And let's wait for the failing test. Only takes 20 seconds. Right, and it fails indeed here. Type of D is not int, it's bool right now. And that's what you probably don't remember, because I was only going over it very briefly. The way to convert an object to int is calling space.int. Where was it here? Ah, no, self.int space, right? And we will steal this approach. It's also what getNumerator and pos and stuff like that do. Right. So sorry, here. So instead of returning self here in the first element of the tuple, we return self.int space. Right. And we can but don't have to look at what int does, but let's do it for curiosity's sake while running the test. So if the type of self is already int object, we just return self. And if the instance has an overloaded __int method, then we return that as an int val, and otherwise there's some base implementation that we can call. Right. Right. Let's wait. That has a better chance of working, and the first variant of the test is already passing. That's promising. And I suspect that the other one is going to pass as well. What is the second? All right. It runs the test again using some slightly different space configuration, which might or might not be useful. Right. Let's run the whole file. And while we do that, we can look at the diff. Right, we added a test with a number of cases. 4 gives 4, 1, -1 gives -1, 1. Something that is a long still works basically. Wait, no, this is a boring test. We should fix that. Here, for true, we check that the result is 1, 1, and that the type of the first element is int. The same for false, except that the first element is 0. And then we have a subclass of int, and we check that it gets converted into int. Right, and then the implementation is rather simple. We add a method on the implementation level, and what it does is it converts self to an int, and as the denominator, it always returns 1. And then there's this connective entry that says that if you want to call the application level as integer ratio method, you need to call this implementation level method. Right. There's actually one thing that we're missing, which is the docstring. Right. And the docstring gets added by adding a docstring to the implementation method, and then there's some magic that that takes that and converts it into a docstring on the upper Python level. Right. Okay, and we implement all these cases, or something close enough, so I think we should be good. Right. Okay. Okay, that's a commit. Done with task number 1. Okay, let's implement cool. Did we run the whole int object test file? Yeah, we did. Excellent. Okay. Yeah, that's basically it for the first task that I had in mind for tonight. I'm also going to demo while we're talking about implementing objects. There is a sort of a playground for fiddling around with that kind of stuff, and it's called bin PyInteractive. It's a very, very, very slow version of Python, because what it does is similarly to the tests, it runs PyPy, which is written in Python, so it can run on Python 2, and that's how we run our tests. But we can also get a console, an interactive console that works that way. So we run Python without translating it to C, without doing any bootstrapping stuff, as a Python program on top of Python 2. And it takes quite a while to boot because it's a very, very slow interpreter. It's like 2,000 to 3,000 times slower than CPython. But the cool thing is that we can inspect stuff on both of the levels and sort of play around and sort of try to see how the levels interact. And yeah, it takes a while to start, but I'll leave it running in the background. And once it comes up, let's play around in there a little bit. Right. While we wait for that, we can look at the second thing that I want to implement tonight, and that's no, that's not that. This is the assignment expression PEP. Okay, then not PEP. Issue, but I can also just show the problem. So the question is what the evaluation order of dictionaries changed, I think in 3.7, and but the dict comprehensions were not changed in lockstep, and you can see that I think with something like that. So input colon input, we have a dict comprehension for I in range 2. Let's make it a dictionary of size 2, and let's call input for both the key and the value. So let's say key 1, value 1, key 2, value 2. Right, and then we get a dictionary as we expected. Key maps to value, key 2 maps to value 2. That's on 3.8. But on 3.7, I think, if you run the same thing, key 1, value 1, key 2, value 2, then you will get a very confusing answer, because before 3.8, the evaluation order here was let's first evaluate for every run of the iterator here. Let's first evaluate the value and then the key. Yeah, and that leads to this very confusing result, because usually Python evaluates sort of roughly from left to right if there's no operator precedence in the way. And so for dictionaries, it was done in this somewhat confusing sort of wrong direction, and that was fixed in 3.8. And we to understand that better, let's look at the bytecode that is generated. Because we're going to, I'm not sure whether we have to touch bytecode generation again, but we might. So let's define a function that does that and then look at the bytecode for that function. So this is in 3.7, and then if we disassemble this, we get the following bytecode. The outer byte, the function bytecode basically calls the dict comprehension code object, which is down here, which builds a dictionary. And then it has a for loop, and in the for loop it calls load global input. Then it calls the function load global input, calls the function, and then does map add. Right, and I think the thing that changes the map add bytecode, because map add would basically first pop the value and then the key and add it in that way. And now it's going to be the other way around. Actually, we need a slightly more interesting example to really understand the difference. And I'm just going to call some non-existing functions here, h colon g. Let's do it alphabetically. G colon h. Now we can't run that because the functions don't exist, but we can disassemble it. Right, and here we see that it calls h, and then it calls g, and then it calls map add, and that's wrong. And indeed in Python 3.8, if we define the same function and disassemble that, now it will call g first and then h, and map add, basically the implementation of the map add bytecode changed to do it, to pop the elements in the other order, because otherwise you swap them, which would be wrong. Right. So this is basically what we need to do. We need to change the implementation for dict comprehensions to call the key first and then the value, and also change the implementation of the map add to pop them in the other order. Let's maybe write a test. What could a test look like? Because input is impracticable in a test, but we can have a list and then say l.pop colon l.pop for I in range 3. It's a nice function with a side effect, and then we get it from the back. 6 maps to 5, 4 maps to 3, 2 to 1, right? And in the old, in Python 3.7, that didn't work. Right. So this shows the problem, and let's see in PyPy 3. This is a 3.6 based one, but I think in 3.7 it was the same. We get the wrong behavior still, so we need to fix that. Right. Thanks, Panos. Right. So now we have an example where we see the differences in behavior, and we're going to basically turn that into a test. Right. And the test. We have a prompt here. I'm going to leave that until we have a next little break. So let's run the test in here. We're done with these for now, so I'll close them. Interpreter, AST compiler somewhere, CodeGen, I suspect, and the test will go to test compiler, which is also where we worked a lot last week. Right. Right. Let me actually. Right. Okay. Where's the walrus operator? Right. Let's put it close to that, I think. Right. Somewhere here. Okay. So test dict comprehension evaluation order self, and basically we plop the code in here that we had. Where is it? The list. Let me actually check whether there's a test file that's no, there isn't really a test file for comprehension, otherwise we could have put it there. Right. So this is our function, and so we will use this strange machinery again. Oopsie. To run that function through PyPy's parser and then execute it. So we say, okay, we want to execute f, and what we want to get is this. Right. That's basically the test. And I'm going to run it again to see whether it fails. I suspect it will fail. Right. Yes, I need to put this into quotes. That's the error that cost me 15 minutes last week. Right. Yes, if I'm too fast at any point, please just stop me. I mean, particularly if you're there live, I'm absolutely happy to go into the details of questions and explain something more slowly. I know that I've been doing that this stuff for way too long, so I'm probably quite a bit too fast in some situations, and also I sometimes talk too quickly and mumble too much. So if it's helpful or you need some more details, please always feel free to interrupt me. I'm trying to keep an eye on the chat. Right, and we get the wrong order basically. So that's good. We have our failing test that shows the problem. Actually, before I immediately launch into this test, I started with dict comprehensions, but I want to go and make sure that I'm not misunderstanding something and what actually happens to dicts, not even dict comprehensions. So if we have a list, let's do the same pop trick again, and we don't have a comprehension, but really just literal dict. Then we get 4 maps to 3, 2 maps to 1 as expected. And let's try 3.7. Actually, let me put that into a paste-friendly one-liner, since I need to. Right. So for literal dicts, this was already fixed in 3.7. So I suspect that in PyPy, for literal dicts, it's also already fixed for. I have a 3.8 built here. It's also already fixed for literal dicts, right? So we're fine here, but for the comprehensions, it wasn't fixed in lockstep. It took an extra version to basically make them sync up again, right? Okay, so we have a test, and we understand that we really only need to focus on comprehensions, not on dict literals. So we can look for comprehensions here. Right. Yeah, I mean, that's also, Panos, that's also something that you can do. If you want me to dedicate a stream to a specific topic, let me know. I'm open to suggestions, and yeah, if there's something you want to see in particular, just let me know. Right. Okay, so here we have a dict comp AST node, and we have a couple of methods on there. We have a build container and load iter, and it calls build map and then comprehension load iter, and then accept comp iteration, which is what is called for every element, and here we see the problem. It calls value walkabout and then key walkabout. That means it first generates code for the expression that is the value, and then code for the expression that is the key, and that's the wrong way around. And is there any, and that occurs twice, I think, yes. There's another place where map add is used, and that is in a slightly different place. Right. So we need to fix them both, and we also need to fix the implementation of map add. So let's look at where map add is implemented. Let's grab for it. A number of them, a number of files have it, but there's a file called pyopcode, and that's indeed where the implementation of all the opcodes is. So let's open that and look at the implementation of map add. Right, let's see. First we pop the key, then we pop the value, and then we take the dict, and we peek at the top element, and that's the dict, and then we call set item on the dict with the key and the value. And basically the implementation changes by swapping these two pops. We pop the value first and then the key, and that means in lockstep we need to change the compiler. In all the places where we emit a map add, we need to swap the code generation to emit the value later, second. That means it's on top of the key on the stack, and we pop it first. Hi, plush master. Right. So we swap these here, and now we need to look at the second implementation here. And we basically swap them too, so that the key walkabout comes first and then the values walkabout. Actually, this is a pretty subtle problem here. The code here is complicated. I actually didn't want to go into that code, but it shows that there's actually already a bug in 3.7 maybe, but I'm going to think about that a little bit later. Let's continue for a little bit. Hi, Julian. But yeah, let me add a comment. Right. Okay. So we changed the bytecode generation. We changed the bytecode, and now it should work. Let's try it. We can run the test again. Waiting, and it passes. Very cool. Let's look at the diff. So the diff is really two things. We change something in the bytecode compiler every time we produce bytecode for a dict comprehension. We change the order in which the two parts of the colon are turned into bytecode. And if we do that, then the order of the stack, of the elements on the stack is wrong. So we also need to change the map add bytecode to pop them in the other order. And if we do that, then we fix the following test, which calls a dict comprehension with functions that have a side effect, and so we can observe that the order is different. And that's already it, I think. Right. Let's run some more tests, maybe the whole test compiler file, and see whether that passes. But the diff looks reasonable, and I think that's basically it. Okay, while we wait for that, we can go back to the prompt that I opened 20 minutes ago. So as I said at the time, this bin pyinteractive.py version is a very, very, very slow version of a Python interpreter. It's PyPy without translating it to C, without bootstrapping it to C. That means it also doesn't have a JIT. Everything is interpreted in 2 layers, so it's very, very slow. And it can do stuff like, right. It takes a while. It takes a while because it needs to parse everything. It needs to generate bytecodes for this line, and then it runs it. And running it is very complicated, and so it takes ages. So the reason to, I mean, of course, you would never use that. The reason to use that is it gives you a nice playground to figure out how objects work in PyPy. So it's a nice sort of exploratory environment that is, particularly if you're starting out, trying to see how objects work, then you can use this terminal to play around. Pardon, sorry, what's the reason for what? And I'm going to show a little bit of that playing around. So if you say x equal 12, and let's do a few more, we can have a string, hello, and a tuple, x as none, and maybe a list with bools, with floats. Right. And so there's the magic thing you can do here is press Ctrl C, and then you're going a level down. Now you're no longer in your normal Python environment. You're in an interactive console on the level of the implementation. So that's basically like going from a PDB to a GDB. So now in CPython, this would be like dropping from the Python level to the C level, but in PyPy, both of the levels are Python. So you can drop from the upper Python level, which is a Python 3, to the lower Python level, which is a Python 2, which implements all the Python 3 on top. And now you have access to the same variables that you defined here, but since all of them are now, you're now on the implementation level, they now get a W prefix. So you have WX. And the WX down here is the same, represents the 12 that we defined up here. And now we can see that the number 12 is an instance of wint object that we saw before, and we can say, okay, what's its int val? There's no completion, but it's 12. So it's it boxes machine number 12. And the same for ws, which is a Unicode object, because Python 3's default string type is a Unicode type, and we can let's not do dir, let's do dict maybe. We can look at the kind of attributes that a Unicode object has. It has a UTF-8 attribute, which is just a byte string, because on the lower level strings are byte strings of the bytes, and then it has a length. That's the decoded length, the number of code points, which is 5 because it's an ASCII string. And then it has a weird field index storage that I'm not going to go into. W-tuple is a tuple object with the following elements: int object, Unicode object hello, and a none object. And then there's also L, and it's a list object that uses a float list strategy. That means it specializes in storing floats, so it has the 3 float values here. And now you can play around with that stuff. So there's also a space here, which is this API that you can use to do all kinds of operations on objects, and you can say wy equal to space dot add of x and x, and then you get another int object which is 24. So if we press Ctrl D now, we go up a level again, and we can say what's the upper representation of y, and that's a regular 24, of course. Right, and if we say z, something large, go down, then wz is no longer an int object, By Arthur. Yeah, we should definitely have a button bros stream, which would be very much in the spirit of PyPy. Right, if you go down, it's now no longer wint object, even though the up level type is int in both cases. But on the lower level, one of them is represented as an instance of wint object, and the other one is represented as long object. Right. Let's do one final fun thing with that list. As you see here, I mean, that's not really the topic now, but it's fun to play with. It's a list that specializes in storing floats. So what happens if we store a non-float? So let's say, let's actually add this list to that tuple, right? So we can say space.add the tuple and the list. You can't do that. I thought you can add. You can only extend it. You can't add it. Okay. Okay. Then let's do it. Let's do it on the upper level. It's easier there. So let's say l.append a string, and then if we go down again with Control-C, then we can look at how the list changed, and we see that it's now no longer a float list strategy. It's now an object list strategy, and it needs to box the object. So now, before it was really just the float values, which is very memory compact, but now that we added a string, we need to box them. So it's now a list that stores wfloat objects, 3 of them, and then a Unicode object ABC. Right. So if you're completely stuck and you can't at all figure out how something in some Python object is represented, and grep doesn't help you, then this is a nice tool to do it. So for example, let's say you want to understand how a subclassing of built-in types works. Because a subclass of int is actually quite complicated, suddenly you need to be able to sorry Matti, I'm lazy. This X is very complicated. You can do all kinds of stuff with X that you couldn't do with the 6. You can add your own fields. You can you could have added slots to the class definition. You can take a weakref. I'm not sure weakrefs work here. Yeah, they do. All kinds of stuff that aren't possible with integers. So if you want to understand how that works, you can again do Control-C, look at wx, and you see that it's now no longer an int object, but it's an int object that has that is a user-defined class. It has a dict and it's weakrefable, right? And if you look at the fields of that, you see that it has all kinds of complicated things. It stores a number 12 somewhere because we set an attribute 12. It has a map, which is a hidden class. It knows that it's an instance of type capital X, and it has a weakref lifeline, which means that there exists a weakref to the thing. Right. Okay. Anyway, that was I got really sidetracked here, but yeah, the console is really a fun environment to sort of explore a little bit how various objects are implemented if you get lost and grep doesn't work and you don't know what's going on. Right. Okay. I'm going to leave it open. Maybe we're going to need it later. Whoops. Oh, some tests failed spectacularly. That's sad. I didn't even run them with minus PDB, so now we need wait some more. Actually, before we do that, one thing that we should do. So I'm a slightly bad citizen here. So our definition of the map add bytecode changed, right? Let's remind ourselves. We're context switching back. Let's remind ourselves what we are actually trying to finish, which is the order of evaluation that changed in with map add, the map add bytecode, and we're slightly bad citizens because we changed the definition of a bytecode, but we didn't. I mean, there could be PYC files around that generated bytecodes under the old assumptions, right? So all the PYC files are now dangerous. All the PyPy generated PYC files. And what the proper thing to do if you release is you increment the magic of the Marshall of the PYC serialization to make sure that the old PYC files aren't used. But given that the bytecodes might change a couple of times in the development process, I usually don't do that. We only do it before the release, or quite often not even then. But I'm going to delete all the PYC files that exist. Never write. Sorry, dash name, of course. Right. And the other thing I'm going to delete is there is a is it here? There is the compiled import library, which is also compiled to a bytecode file, and I'm going to delete all of them, I think. Right, empty the cache directory. That's always a slight gotcha. If you're changing bytecode generation, then it can happen that you have some piece of old generated bytecode around that sort of freezes the old world, and then if you try to run that with the new implementation of the bytecode, then you might run into trouble. Okay, right. I mean, I'm not really sure that was the reason for the failing tests, but given that we changed bytecode, we should definitely do that as a precaution. Okay, now of course all our parallel waiting was useless because we need to wait again, and it takes many seconds. And yeah, it crashed in some very annoying way. We can't even debug. Maybe we can at least run some other tests in parallel. Right. More waiting. Yeah, we should run. Yeah, I don't know. I don't know. Yeah, this will take a while. Sorry. I mean, stuff isn't completely broken, but that's also not really that surprising because dict comprehensions aren't that common. So yeah, I mean, if you break a really fundamental feature, then basically immediately nothing works. But dict comprehensions are rare, and dict comprehensions where the order of evaluation of the two sides of keys and values matter are even rarer. So it's kind of expected that most stuff will keep working. But then there were some test failures that we saw, and we'll see they occur in the third line of dots. We're now on the second line of dots. Right, this file passed, for example. Function. Test syntax. Let's run that. We're getting closer to the critical dot position. Yeah, the PyPy test style is often quite heavy on integration tests because we really run stuff on the top interpreter. So all kinds of stuff is, all kinds of things are tested together. We could also imagine a test that is much more unity here, right? Right. We could write a test here that generates bytecodes for this function and then inspects the bytecodes and makes sure that things are generated in the right order. And then we could write a unit test for the map add bytecode where we have a very minimal code object that we just calls map add and checks that stuff happens in the right order too. But yeah, that's sometimes we write stuff on unit tests in that much more granular way, but often we tend to do this more integration test style where we test both the bytecode compiler and the bytecode implementation together, which is also much closer to what CPython does. Right, so test syntax passes. Right. I think we may be past the critical point. So deleting PYC files maybe already helped. So I'm going to commit this. Let's wait for the line to finish at least. Right. I'm going to commit that. It doesn't look half bad. Yes, maybe we can think about this problem. Okay, so this is actually a somewhat complicated issue. The problem is the following. If you have, let's do some bytecode inspection again. And this time let's do it for a very artificial function. The function, we're not even going to write the function, we're going to use string manipulation to define a function. And it looks like this. So we define a function and we return a dict. I have a version of 3.8 around that breaks readline, right? So we want to define a function that returns a dict, and the syntax for the dict is auto-generated, and it looks like this: comma dot join I colon I plus 1. No, %s. Sorry, I'm too lazy to think about how f strings work, which I should really use here. I plus 1 for I in range, something like this. Right. Where did I miss the right here? Right. So this is our function, right? It's a very, very long function that defines a really huge dict, right? Maybe I should do a slightly smaller one. Maybe it's enough to have 2,000 entries, right? And so now if we exec this, we have this function, and if we disassemble this, we get a really scary thing that calls load const many thousand times, and then in the end it calls build const key map, which is a new opcode, which produces a dictionary. The problem of that for PyPy is that the stack depth of this dict of this function is really deep. So if we look at the code object of that, co stack size, The stack size is 2001. So we have to execute this function, which just builds a slightly complicated dict. We produce a code object that needs a really, really deep stack, which in theory is not bad, right? I mean, a stack is just a list, so a list of length 2000 is not a problem. But if we did such a function, then we're trying to generate a function that needs 2000 virtual registers, which really map to the C stack. And so we might blow the C stack. And so for that reason, in PyPy, we generate slightly different code for this kind of function. We generate code that will produce the dictionary in a smaller amount of stack size, right? So in PyPy 3, wait, let me paste this line. If we do the same thing in PyPy 3, we get different bytecode. Right. This bytecode is very different. It doesn't push all the elements on the stack and then makes the dict at the end. Instead, it will make a dict that's empty and then push key and value on the stack and call map add, right? And that means that f.code.co stack size is 3, right? So we do it in a smaller stack size because the stack size of a function maps to the C stack, and we don't want to use gigantic amounts of C stack just to define a dictionary, even if the dictionary is complicated. So, and that's the code that we saw, right? The code that we saw here, where I added the comment here. Right, that code path is basically taken if the number of keys that the dict has is larger than some threshold, and the threshold is 100. So if we have a dictionary that's larger than 100, then we will do it not by using a stack size that's twice the size of the dict, but doing it in a slightly less efficient way, but in a much smaller stack size. And that used the map add bytecode. But it also, what we can also see is that we before we change things here, we evaluated keys and values in a different order. So that means that in 3.7 there's a bug. In PyPy 3.7 there's a very subtle bug. And that bug means that dictionaries that are very huge and where the definition does things with side effects, we would get them in the wrong order again, right? And we can probably observe that. Let's try to write a very devious test. Okay, I'm going back to this. It needs to look slightly differently because we need to define the dict using something with side effects, right? So let's make let's use the dict pop trick again. So wait, I want a string def f and then L equal list of range of 100, and then we return a dict with some content, right? And the dict is basically the dict elements are joined with a comma, and we need it's a list of length. Maybe the list is too small. Let's do 400, and then the list elements are basically l.pop : l.pop, right? And we need that 200 times. Right. Whoops. This one does not match right. It's just broken. Right. Okay. So this is our dict definition, right? We have a list, and then we have a dict where every element is a pop and a pop, right? And if we exec that and call it, we get a dict that looks like this. And let's see what CPython 3.8 does. Is it right? Here we see the problem. 0:1, 1:0. So it's swapped. So right. So we found a very annoying corner case, which is that for very large literal dicts where the definition contains functions that have side effects, Python 3.7 will evaluate them in the wrong order. And I'm not going to fix that now, but I'm going to open an issue to not forget about it. So let's go to heptapod. We're using a fork of GitLab that works with Mercurial. And issue issues. Let's make a new issue. Large dictionary. Bytecode generation is wrong on PyPy 3.7. Example. Should should return the following dict. So this is the correct behavior, and that's what we're not getting. Right. Right. I don't want to fix that now, but we should also not forget about it, so I'm filing an issue. I can assign it to myself. Right. That's a good question. No, it has been useful. We have been using, the question was how much hypothesis we're using. There are quite a number of tests that use hypothesis. But yeah, it's not that easy to write a test that finds this problem. Because, thank you, Matti. Because, I mean, think about how many conditions had to be fulfilled to show the problem. I mean, it's not enough to define a huge dict just with numbers. It had to be a huge dict where the keys and the elements are defined using side effects, and then only then would you observe the problem. So it's not that easy to write a test for that. I think that would catch it in hypothesis. Yes, but how do you generate the dict? I mean, you can't just use the dict generators of hypothesis, because it really needs to be, you need to generate the dict by having a huge dict literal, but the dict literal cannot just contain numbers. I mean, remember that the dict literal is very unnatural, right? It's not like there are numbers in the dict literal here. It's really that the dict literal contains, I mean, it's a completely ridiculous dict literal, right? Because we all the elements of the literal are the same, sort of, apparently, except that they call a function that has side effects, and then we see the problem only then. So I'm not sure how you, I mean, if you can show me a hypothesis test that would have caught that, I'm very interested. But I'm somewhat skeptical. Anyway, right. I wasn't expecting that. I was expecting this to be a very straightforward task, and now we hit this very strange problem. I'm going to remove the comment because the comment was there for to remind myself, but now we put it into an issue to make it more permanent, and I'm going to commit this now. So, hi Tobias, welcome back. So, Twitch. So, fix evaluation order, keys and values in dict comprehensions. Okay, so those were the tasks that I kind of was planning to get to. If there's any specific topic that somebody on the chat wants me to talk about, then please tell me. Otherwise, there's one small other thing that I kind of have in mind that is something that we could look into, and that is that there were quite a number of additions to the math module, and one of them is relatively simple. So we could look into that, and that's the I square root function. It's basically an integer square root function that takes an int and produces the integer that's closest to the square root of that, so that the square of the square root is below the argument. Do I have the? No, I don't have the. I don't have the BPO open, but we can grab around for how it works. So this should be small and not so bad. So let's try to do that. Actually, it's also nice to do it because it gives us a kind of a third area of PyPy to look into. We looked into today a little bit into how objects work and a little bit into how bytecodes are implemented. And now the third thing we can look at is how modules, how the built-in modules are implemented. But let's start with CPython. So I'm going to my CPython checkout and grabbing for square root and advanced. Right. Fairly, yeah. I'll open this in a tab. Right. So there's a documentation. There's a test. Let's look at the test first. And then there's code in math.module.c. Wait, that's useless. Sorry. Okay, I square root. Right. Test a variety of input, large and small. So we have some numbers, and the test basically is that the result is an integer, and we check that as the result times the result is below or equal the argument. But if you take the next larger square, then it's larger than value, right? That makes sense. And we're just going to steal that. And down here, there are a number of corner cases, like what happens if you use an int-like thing like bool, which is something we already did earlier. You still get an int out, and it should be equal to 1, and false the same, and blah, blah, blah. So we're going to steal those tests. Let's start very simply. The modules are in a subdirectory called module, and we can go to math. It's here, and then there are tests in here. So let's open those. Math test math. Right. And there are app tests. I'm going to say again what that is in a moment. And so we can go to the bottom and say def test I square root. And let's start with a really, really simple test. Import math assert square root 9 equal 3, and type of x is int. Right. I think that's basically what we want. And if we run that, it will fail, of course, because we didn't implement the function yet. Oh no, math square root. Right. And while we wait for that to run, we can look at the implementation here. Right. Integer square root, blah, 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 lots of text. Here's the Python code equivalent to the C implementation below. Okay, that is fantastic. So here is a pure Python implementation of what we want to achieve. And sketch of proof of correctness, very interesting. And then there is the implementation here. And the implementation looks very scary. It's super annoying. It uses all these pylong functions. So pylong sign, pylong num bits, and then it has loops and rshift, and it's completely unreadable. But the author was extremely nice to us, very, very helpful, by giving the Python code here, right? Because we can use that pretty much directly. Right, so we get the error, math has no attributes, I square root. So now we need to understand how we add implementations to like functions to a module. And for that, in every of the module directory, there's a file called module def. And that basically is defines how the that defines how the module content is where it comes from, right? And there are two dictionaries here. There are the interpret level defs and the app level defs. And the interpret level defs are stuff like GCD. So this mapping here says the application level function called math.gcd is implemented by this function on the RPython level, right? And that means to look at the GCD implementation, we look at the interp math file, which is the interpreter level math implementation, and then there should be a GCD, which is the greatest common divisor method, and it looks like this. Yeah, hi Robin. I'm going to tell you in a moment. Let me finish that thought about the greatest common divisor here. Right. So that's the implementation, and the implementation looks. Is in RPython, right? And it takes a wrapped A and a wrapped B, and it turns them into integers using the space.index method, and then it takes the absolute value of them using the space.abs method, and then it tries to turn them into integers, and if they fit into a machine int, then we have a fast implementation using this function GCD binary here. The result is an int. We return it into a wrapped int again. And if one of them is a big int, then we need to use a slightly slower implementation, and we call a.gcd on the big integers, and that takes longer because they're larger. And then we return the result by wrapping the resulting big integer back into a wrapped long object. Right. So that's the RPython code. Yes. Tobias, exactly. That's exactly the plan. There's also the other kind of function definition here, and that's the so-called application level definitions. And the code that we saw here is in RPython, which is Python 2 based, but there are also app level definitions. Sometimes we're too lazy to do all this work that you saw here of calling all these weird space methods. Sometimes we just want to write completely normal Python code. For example, for factorial. For factorial, it's easy to write in Python. So we just wrote it in regular Python code, which is Python 3, no problem. And then you can just write, do all the tricks in the book and write all kinds of Python code that you want, and it's easy to debug, and you just put it here and you're done, right? And now we have it extra easy because we have some regular Python code. because Mark Dickinson was really nice to us. Mark gave us some a Python implementation here, and we're just going to steal that. So we're going to take it and put it here. And dedent it. Right. And now we go to the module definition. Robin, I haven't forgotten you. I'm going to get back to your question in a couple of minutes. And now I'm saying that I2 is implemented in the app math module I2. Right. So it's the function I2 in this file here. And this file is a regular Python 3 file that runs on top of the interpreter. So it's not compiled to C or anything like that. Right. And we know that it works because, I mean, we know that it works because the author of I2, who did all the complicated work of proving that the algorithm is correct, gave us this debugged and nice Python version of the algorithm, and that means we don't need to do any work. Yes, so now Matti is cheating and explaining everything. Yes, exactly. So it's, whoops. Oh, I didn't save the file. Your gut feeling is correct that that it sounds like it should be slow, right? We're implementing in Python, so you always need a lower Python and then the Python and then the actual code. So there's a double interpretation overhead, and that sounds like that should never be ever fast. But indeed, as Matti is explaining in the chat, we are not writing it in the full Python language. The interpreter is implemented in a subset of Python, and the subset of Python is called RPython for restricted Python. And the subset is chosen in such a way that you can take the interpreter and you take the interpreter written in RPython and you bootstrap that to C. So we have another program that takes RPython code and compiles it to C code, and then that doesn't work for every kind of Python code. It only works for a specific style of Python which we call RPython, and then you take the interpreter, you translate it into a C binary, and then you got rid of the sort of double interpretation overhead. That's still not fast. That still only, quote unquote, gives you a binary that is an interpreter for Python in C. And it's sort of roughly comparable to CPython. Usually it's quite a bit slower because CPython is quite well optimized. But while we translate stuff to C, we can also automatically compile in a JIT compiler into the binary using a tracing JIT technique, and then we have a JIT in the binary, and that produces machine code at runtime for the user's Python program, and that is quite fast. So there are basically various components to the puzzle. One of them is we write it in RPython, which is bootstrappable to C. And then the other component is that we add a JIT compiler, which produces machine code at runtime for your Python code. And that's how it becomes fast. Right, okay, so back to the test. We have this problem here, name operator is not defined, right? And that's weird. I mean, the error is in this line here. We don't really see where it comes from, but if we run it with minus verbose, we should get a little bit more information about the source of the error. I hope that works. And then we should see that the error really comes from, no, we don't. Okay, but the error obviously comes from this function here. So this uses the operator module, and I didn't import it, so let's import it here. Anything else that isn't imported? So maybe we have better luck now. Blum, blum, blum. While we wait for that, we can steal some more of the tests. I'm not going to test all those corner cases. Yeah, that's Robin. That's a normal reaction. It takes a while to wrap your head around all this stuff. Particularly since it's really several things that happen. I'm not going to test for all the corner cases. I mean, in the end, we're also running this test on top of PyPy, so we will catch the problems, more complicated problems later. But I'm going to at least do what they do here, and run a few of those tests. Right. So let's change it to PyTest style. Assert s times s less equal value. Assert value less than s plus 1 times s plus 1. Oops. Okay, value is wrong. Value. Maybe that's a bit too many of them. Let's see. It's possible that those tests take way too long, but we can start them. Right. Yeah. Why is this cool? I mean, so actually, I cheated a little bit, and cheated. I looked into this a little bit this afternoon. I wasn't planning to get to it at the stream, but the other things didn't take as long as I thought, so we have some time for it now. I actually experimented with how fast that code is, right? I mean, in some way we're really stupid. I mean, this looks like it could never be efficient, because we're comparing Python code against nicely hand-optimized C code here, right? CPython has a very careful implementation of I². Here it's all written in C. It should be super efficient, right? Yeah, right, Matti. That's exactly what I'm pondering now. But this is application level regular Python code. That means the JIT will compile it, right? And so the question now is, if you take this function and let the JIT compile it, will that compiled function be faster than the manually tuned and handwritten code that the CPython authors wrote here? And I tested this exact question in the afternoon, and it turns out that PyPy the JIT is massively better at turning this function here into machine code than the C code that is part of CPython. So we can look into that. Where was I? Here. So I wrote a benchmark here. It's really hacky. I don't want to go too much into details here. What it does is it basically calls the I² function for integers of different sizes, right? And then measures the time of doing that. And then if you do that on PyPy, so the output that you see here is every line is a benchmark, and then we have a benchmarks with bit size 50, so that's integers that still fit into a machine word, and then it takes 78 milliseconds to run the test. And it's not very scientific, and I'm not computing, and I'm not rerunning the benchmark, and I'm not getting an error, but sort of as a rough rule of thumb, we can believe these numbers. So for bit size of 50, we take 80 milliseconds, and for bit size of 150, we take 386 microseconds, and so on. And then we can run the same thing on CPython. And on CPython, we can run it in two different ways. On CPython, we can also run the Python code, or we can run the C code that's built in, right? And so at first, we're running the Python code, right? And of course, the Python code is very slow. Actually, maybe it's so slow that I don't want to wait for it finishing, but let's keep it running for a little bit. So what we see here is for the bit size 30, it took PyPy's JIT 60 milliseconds to run the benchmark, and then for CPython 30, it took us 700 milliseconds. So that's not so surprising. If you compare PyPy, which has a JIT, to CPython which doesn't, and it's sort of numerical code, it's not so surprising that CPython is roughly 10 times slower, right? That is sort of apples to apples. But then in the second half of the CPython numbers, which I'm going to interrupt this now and edit the file, we can also compare it against the C code that CPython has built in, right? So, and that's the second loop down here. If there is an I2 in math, we're calling that. And so I'm going to comment out the first loop. And now we're comparing against C code, right? So we're comparing pure Python code written in completely regular Python against manually tuned C code that is optimized by GCC. And it turns out that we're also 10 times faster. And that is a slightly annoying result for CPython because, yeah, I mean, it really shows that the JIT can be much better at numerical algorithms than even the C compiler. And it's probably not true for all the cases, right? If you have really huge integers that have tens of thousands of digits, maybe then the C code becomes better. But sort of for numbers that fit into a machine word, we're definitely much faster. And for numbers that aren't too huge, so let's check one. So bit size 200 takes 1200 milliseconds on CPython, and bit size 200 takes roughly 400 milliseconds on PyPy. So yeah, we're faster, sort of. I mean, probably not everywhere, but in a number of the phase space. So yes, Julian, this is a very good question. The question is why, right? I mean, this seems really counterintuitive, and the reason for that, I think, is that all the C code here is using longs, right? It's using long R shift and long L shift and PyNumber add, which is adding longs, and longs are not machine integers, right? It's doing all the computation using wrapped Python longs, and they have a few fast paths for machine word sized integers, but that still means that every intermediate addition that is done here allocates a new integer on the heap, and it increments its reference count, and then it does some more reference counting manipulation here, and then it calls PyNumber multiply and blah blah blah, right? So there's a lot of overhead by shuffling around the Python numbers, and that overhead is pretty costly. And the DIT is much better. The DIT will recognize here in this code that, oh, our number happens to fit into a machine int. So we really remove all the object overhead, and we will not do any allocations. We will really do all of these operations directly on the CPU without faffing around with reference counting or garbage collection or any of that stuff, right? So we all of these operations become much faster. And for CPython can optimize more to catch up, right? They can by having two implementations of square root. One for arguments that fit into a cint, that would be faster, and then one for arbitrary long integers, and for that they're using the C API. Yes, but Matti, they have to use the C API because otherwise it doesn't work for arbitrary large ints, right? I mean, they could have a fast path for small integers, like for machine-sized integers, but yes, exactly, Robin. They should write a fast path for small integers, but they haven't so far, right? Since they haven't, we're beating them badly. And once they add one, they're probably faster again, because if you really compare algorithms that just do sort of machine integer operations, then of course C is much faster than our JIT, because our JIT has a slightly crappy code generation and a slightly not so good register allocation and all that kind of stuff. I'm not really saying that we're always faster than C. What I'm saying is that with very little effort, we can be faster than sort of write C that is not super optimized. Matti, that's not. There's actually a surprising number of integer functions around nowadays, like GCD, and there's even another function that we're going to have to implement soon, which computes integer reciprocals modulo some relative prime. And so nowadays the math module has a number of integer operations, and I suspect all of them are faster than CPython, unless they really wrote a fast path for and wrote everything twice, basically. So yes, I was happy when I ran my crappy benchmark this afternoon. I was happy with the results. Okay, so I'm concluding that there are way too many cases in the test because they're still running, even though I was talking your ears off. So let's actually do that for a lot less cases, right? Test values equal range. Oops. Could Vim please wake up? List range. I don't know, 10. And plus, let's use one large number, -1 maybe. Right, and then also let's add a assert with raises. What does it raise? Value error, yes. Right. Yes, this is absolutely. This is a fantastic example for hypothesis, and I mean, it would probably make sense to there is a repository that collects hypothesis tests for various functions in CPython, and it would be a great addition to that repository. Right. By the way, what I saw earlier in the comment is something that I want to show, because it shows the extreme dedication of Mark Dickinson, which is that he actually wrote a machine check proof for the correctness of his algorithm. So this is, and I'm showing it because both Julian and I have a sort of passing interest in this language, which is called Lean. That's basically a dependently typed language that allows you to formalize the correctness of algorithms and also to formalize all kinds of mathematics. And there's this amazing 800-line long proof that shows that I square root is a valid square root. So what's the theorem? It shows that if you have a natural number and you take its I square root, which is defined up there, then the square of that, the result is smaller or equal to n, and n is smaller than a plus 1. Yeah, Lean is like coq. Lean is like is rather close to coq. So the Lean community is really heavily into doing pure mathematics and not so much using it for applied stuff like what is used here, but apparently Mark knows it, and I'm very impressed. Right. Okay, the test passes. Right. Excellent. Okay, I think I'm going to stop very soon. So we did 3 things. We implemented the integer method as integer ratio. We fixed the evaluation order of keys and values. In dict comprehension, finding a pretty annoying bug in 3.7. And then the last half hour, we implemented math.isqrt at app level. And yeah, that's 3 relatively small, nice additions to our budding 3.8 implementation. Right. Actually, so for the people listening that didn't do a lot of PyPy contributions yet, there are a number of other math functions in that style that were added in 3.8. So do I have the math open? New in version 3.8, right? There's stuff like math.com, which is the combinations, and I square root we just did, perm, prod, dist, and yeah, that's it. And all of them are probably not super hard to add, so all of them would make fairly nice first contributions. So if somebody's interested in giving PyPy contributing a try, those are very good candidates. Right. And I think actually, which of them? I think at least one of the other ones also has a nice Python implementation that you can just steal, and I'm not sure there are more that have lean proofs. No, that's the only one that has a lean proof. Okay, so if there's any question, I'm going to hang around for another minute or two for them to wait for them to show up. Otherwise, I think I'm done for today. Julian, did you just mention me in the lean chat? Excellent. Okay. So thanks everybody for showing up today. And actually, maybe we can raid Yeah, we can probably raid Anthony. Let's do that. It's all Julian's fault. So thanks everyone, and see you at the next stream.